we go. If you didn't, we are still going to go through this lesson. I was just hoping to go through it maybe a smidge bit quicker than usual because people will have written stuff down already. Anytime we're looking at a chemical system that's at equilibrium, there's a constant ratio between the concentration of the products and the concentration of the reactants. It doesn't mean that nothing is changing. So remember, just because we're at equilibrium doesn't mean things have stopped, just that products are turning into reactants and reactants are turning into products at the same rate at the same time. So in any equilibrium system, Kc, which will be our equilibrium constant, can be calculated by taking, and if you look at the letters, the concentration of the products divided by the concentration of the reactants. The exponents in this expression are the coefficients in the balanced reaction. Now, does anyone have questions about the general form for an equilibrium law expression? Because then there are a bunch of examples that go with it. Okay. So there are some rules about what you do and what you don't include in the equilibrium law expression. Any reactant or product that can have a changing concentration is included. So what this is telling you is that some things, usually because of their state, can't change their concentration because we couldn't measure their concentration. So in these two examples, everything is a gas. Gases would always be included in the equilibrium law because the concentration of a gas could change the minute that the volume of the container changes. So it's realistically possible for that to happen. So in those two examples that are up there, if I were to write the equilibrium law expression, which I will do, maybe, there we go. I always need to take products first. So this mimics Hess's law in the sense that products come first when we're doing the calculation. So I would take the concentration of CO2 times the concentration of hydrogen and divide it by the concentration of carbon monoxide and the concentration of water vapor. Now, in a lot of reactions, the coefficient for a lot of substances is 1. So there would technically be a 1 here. That means that there would technically be an exponent of 1, but anything to the power of 1 is just that same value. So you don't need to include it. The other example has substances that have coefficients. So when we set up the equilibrium law expression here, we'll take the concentration of SO3 gas, but to the power of 2, because the coefficient was 2. So if there's a coefficient in the balanced reaction, it becomes the exponent in the equilibrium law expression. My reactants would look similar. I'd have SO2 gas to the power of 2 and my oxygen gas concentration. Even though it's not indicated, you need to pretend that there are brackets on the bottom so that you multiply together everything that's on the bottom of the equilibrium law expression before you divide things. When you're just setting up the expression, it's not a big deal, but when you're calculating it, it really is. If you look at what's on the boards at the back, my grade 10s, bless them, are calculating things like kinetic and potential energy. And in some of the formulas, especially if they're manipulating them, they have 2 terms on the bottom, and they always forget. You got to multiply them together before you divide them. But it makes you get the wrong answer, even if you have the correct work, because you're not sure how to use your calculator. So just a little warning there. Now, other things that could have a changing concentration are anything that has aqueous as its state. If something is aqueous, AQ, it means it's dissolved in water. I could change its concentration if there were more water or more of the substance. So AQ is a state that you would include. So the equilibrium law expression here would just include the concentration of my product ions divided by the concentration of my reactant molecules. Now you might think this is weird. We're doing a chemistry formula and we're not actually calculating anything. Quite honestly, there will probably be a diploma question where all you have to do is identify what the correct equilibrium law expression is, maybe not even calculate with it. So it really is important that you can set the formula up correctly. Now the next thing is to show you some substances that do not get included. So pure solids are never included. I don't like to use the word never unless I mean it, so I mean never. You don't ever include them in the equilibrium law expression. So if something is solid, we're not going to include it in the equilibrium law expression. Doesn't mean it's not there, that it's not part of the reaction, but when we're talking about equilibrium in particular, it's not going to play in our calculation. So when I set up this equilibrium constant, I know I'm going to have H2O gas concentration and CO2 gas concentration. I'm not going to include my sodium carbonate because it was a solid, and I don't have any reactant to include. So what goes on the bottom? A number 1. You don't even have to write it. You can just leave it empty. You could just write this part here. So if the reactant is a state that we don't include in the equilibrium law calculation, then it's possible that you don't have anything on the bottom of the expression, and so you don't have to write the 1. In the other example, it's our product that's a solid, so it's not going to get included in the equilibrium law expression. Here we have to put a 1. I can't have a fraction with no number on the top. So my numerator has to be something. If the denominator is 1, I can take it out. But here there has to be something on the top. And then on the bottom, I would have my 2 reactants concentration. Noticing that there was a coefficient of 3 in front of those fluoride ions. So the exponent would be 3 in my equilibrium law expression calculation. Now, does anyone want to ask any questions so far? Things that you should or shouldn't include in your equilibrium law expression? The next thing is about pure liquids. And notice I didn't use the word never, I used the word not, because there's an exception. As a general rule, we don't include pure liquids unless everything is a liquid. So in this example, water is a liquid, not going to include it. The fact that water is a liquid will be really important. Later we'll talk about acids and bases, and water is always around when we're talking about acids and bases. And often incorrect choices on a diploma exam will be an equilibrium law expression where water has been included when realistically it shouldn't be. So if we write our equilibrium law expression here, we would write 1 over the concentration of H2 gas and the concentration of O2 gas. Now, if you have a scenario like the one that's there, and if you look at what's going on, everything is a liquid, not aqueous, but actually an L for liquid. If that's the scenario, every single thing in the expression is a liquid, then you include all of them. Yes, you're right, it would. Thank you. Now, in the reaction where everything is a liquid, perhaps someone could tell me what just happened there? It's what we just went over in the last unit. So I have C6H6, some kind of hydrocarbon. I add bromine. I end up with something where there's one bromine with the carbon. Yeah, it's a substitution reaction. Uh, Benzene being around is probably the only scenario where everything would be a liquid. Benzene and bromine are liquids and they can react with each other. So this is probably the best example that I could give you. I would think that this exception would come up really rarely. Usually it doesn't come up at all, but just on the off chance that it does, because we could combine an organic question with this, that's how it would look. Now, we can calculate the equilibrium constant. So just setting up the expression is one thing, but actually calculating it is another. We want to know the equilibrium molar concentration, and by that I mean moles per liter. We always want to be working in moles per liter because that is the standard unit. All we have to do now is substitute each of those into the equilibrium law expression. So, if I read the question up here, it tells me that nitrogen monoxide gas reacts with oxygen, which I know is O2 gas, to produce nitrogen dioxide gas. I put the equilibrium arrows because it says at equilibrium, here's what I got. I need to check and make sure if this is balanced though. And the way that it is there, it's not balanced. Anyone want to tell me what I should do to make this reaction balanced? Yeah, I should put a 2 here and here. So in front of both of the ends, I should put a 2. When I do that, I have 2 nitrogens and 4 oxygens on both sides. Yes? How do I know, sorry? Because it said we're talking about equilibrium. A redox reaction would be complete transfer of an electron. Anybody else want to ask anything there? Now, because we're at equilibrium, and it's already given me the equilibrium concentration, remember we learned about how to make an ice table? We don't have to here, but I could see how a person could have to do that in a calculation. In this case, we already know the equilibrium concentration for all of them, so I don't need to make an ice table, but I do need to set up my Kc expression. I will take the concentration of NO2 gas squared and divide it by the concentration of NO gas squared and the concentration of O2 gas. Super important that those terms on the bottom all get put together before we divide them. So when I substitute numbers into the expression, I would have 0.094 moles per liter squared divided by 0.017 moles per liter squared times 0.053 moles per liter. Now, the equilibrium constant does not have a unit, and you'll see that as we go through this entire unit. I'm taking moles per liter, squaring them again, dividing them. Who knows what weirdo unit we're going to end up with. So when you write your answer to an equilibrium law expression, don't put a unit. You'll see that when values for K are given in the data booklet or on a test or part of a question, there won't be a unit, and that's why. Now, if everything has gone correctly in your calculator and you do this, you should get 576.875 as the answer. If I look at my digits here and I think about significant digits, all of my equilibrium concentration values had 2 significant digits, so that you know the question will always tell you how many digits should be in your answer. If it's an exam question, it'll say, put your 3-digit answer in the numeric response section, or put your 2-digit answer there. Because all of these have 2 significant digits, I too will do that. So I will put 5.8 times 10 to the power of 2. Most of the time, KC values are written in scientific notation like this. This is a pretty small KC value. Some of them can get really massive or really, really tiny, but they're almost exclusively written in scientific notation. All right, folks, we are going to continue so that we can finish. The next part directly addresses the question Nicholas asked me just before the break. What does it mean? Like, why would we calculate this? So that's what the next few points are about. Essentially, what we're going to use KC for is to determine the position of equilibrium. And by position of equilibrium, we're talking about product versus reactant. And so the terminology that we'll use is we'll use the word favor. So if I say that a system is favoring something, it means that there are more of them. So some systems favor the reactants. That means at equilibrium, there's proportionally more reactant than product. Now, what will you see if this is the case? KC will be relatively small, so smaller than 1. I don't mean negative. When I say smaller than 1, think about like 0.001. That's smaller than 1. The number shouldn't be negative because I shouldn't be measuring negative concentrations. So when I say smaller than 1, I mean a decimal number that's between 0 and 1. The other thing that you might be given as a piece of data is the percent reaction. In this case, less than 50. So less than 50% of the reactants became products. So if KC is really small, that's what we know. There's more reactant than product. They are the favored side of the reaction. If we're thinking about what it means to be favored, think about a teeter-totter. It's the heavier person on the teeter-totter. It's the side that's favored. Now, if KC is relatively large, then we're favoring the products. That means there's proportionally more product than reactant. When KC is relatively large, i.e. larger than 1, and the percent reaction is greater than 50. Now, there are scenarios where there's more reactant. There are scenarios where there's more product. And then there are scenarios where there's still some of both of them in relatively equal quantities. So in this case, we wouldn't say that the reactants or the products are favored. So in some systems, neither is favored. In other words, there's roughly equal quantities of reactants and products. And when we say quantities, we're talking about moles. That's what we mean in chemistry. In this scenario, KC would be very close or equal to 1, and the percent reaction would be very close or equal to 50. Now, very close is not a very definitive term. So if I'm going to ask you about this, I try to make the number so far away from 1 or so far away from 50 that you couldn't misinterpret what it means. The value of KC is something that is temperature dependent. So when we calculate KC, we can't change the temperature and assume that it's still true. So whenever we calculate a value, it's always for the temperature that the substances were at when we did the calculation. Another thing that's true is that the value of KC does not determine how quickly equilibrium is reached. So it doesn't tell us anything about how fast the reaction happens. It's just telling us that when the reaction has gotten to its equilibrium position, maybe that took 10 seconds, maybe that took 10 hours, but whenever it got there, that was the position of equilibrium. So don't misinterpret a large Kc as a quick reaction. That's not what it means. They could both be happening, but just because Kc is large doesn't mean that the reaction was fast. Now, percent reaction is one of the things that you could use to determine which side of the reaction is favored. Percent reaction is where we compare the potential product yield that we could get if the reaction were quantitative. When we're talking about equilibrium, the whole point is that the reaction wasn't quantitative. It didn't complete. All of the reactants did not become products. To figure out a percent reaction, we're going to imagine that they did and figure out what would have been the maximum if it were quantitative. So the formula is up there. To figure out a percent, you figure it out the way you would figure out any percent, like your percent on an exam. Take what you got, divide it by the total, multiply by 100. Here, we'll take what we got, divide it by the maximum total that we could have got, and multiply by 100. So in this question, we'll actually review a few different things. First, we'll take a look at what the reaction is. The formation of hydrogen chloride gas. So if I think about what that would look like, I know that HCl gas is my product. And it didn't say what the reactants were, but if I keep reading, it says I put hydrogen and chlorine gas into a container, so that must be what I had. I added a 2 because it wouldn't have been balanced if there weren't a 2. Now that I have my expression, I can write my equilibrium law, where I take the product concentration squared, because the coefficient is 2, divided by the reactant concentrations, not squared because their coefficient is 1. Now, it tells me to calculate Kc and the percent reaction. And so I want you to be really careful when you're calculating Kc. This represents equilibrium. I don't know what the concentration at equilibrium is for either of those or for any of those gases. I know what I had at the beginning, and then I know what my product is in terms of concentration at the end. So to calculate Kc, first I need to do an ice table to figure out what the equilibrium values actually are. So it says in the question that I'm putting 0.4 moles of hydrogen and 0.4 moles of chlorine into an evacuated 500 milliliter container. So one of the things that you must remember is that this is how you calculate concentration. Sometimes the container is 1 liter and it makes your life easier, but in this case, the container is only 500 milliliters, so I'm actually going to have to calculate the initial concentration. So, for example, 0.4 moles divided by 0.5 liters. Now that should tell me that the initial concentration is 0.8 moles per liter. I'm maintaining my 3 significant digits so I don't forget about them later on. It says the container was evacuated except for those two things, so the initial concentration of HCl is 0. If you'll recall, I know it was a long time ago, we need to know at least one equilibrium concentration, and we do, 0.28 moles per liter. Since the HCl concentration increased, the other two had to have decreased, opposite sides of the reaction. HCl has a coefficient of 2, so it would have increased by 2x. Hydrogen and chlorine have a 1, so they would have decreased by x. We would determine that x is 0.14 in this question. That way 2x really gives me 0.28. And that would tell me that the equilibrium concentration is 0.66 moles per liter. Now that's really what we did in lesson 1. Does anyone have questions about that part? Now that I know the equilibrium concentrations, I can take those values. This one goes up here. Those ones go down at the bottom. But now I can calculate Kc using the equilibrium law expression and those values that I just calculated. So my Kc will end up being 0.28 squared divided by 0.66 times 0.66. Now I should end up with 0.18 as my value for Kc. The other part of this is to figure out percent reaction. So if I want to figure out percent reaction, I need to take the equilibrium product yield. So that's my 0.28 moles per liter, what I actually had as my product at equilibrium. I'm going to divide that by the most that I could have gotten. So if you think back to Chem30 and you were thinking about stoichiometry and how to figure out what the limiting reagent is, you might have used some of these principles. But if I start with 0.8 moles of hydrogen and chlorine, there's an amount of HCl that I should get in the end. If I look at these initial values up here, if this reaction fully, completely happened, where every single one of those 0.8 moles per liter was converted into product, the coefficient here is 1 and the coefficient here is 2. I should have twice as much product as I started out with reactant. So I should have been able, maximum theoretical, to get 1.6 moles per liter. All I did was take one of my two reactants here, since they both had the same concentration, either one of them could have been the limiting reactant, and compare the coefficients. The coefficient was 1 there versus a 2 for HCl, so I multiplied it by 2. That was my maximum theoretical. We multiply that by 100, and it gives us 17.5%, or we could just round to 18%. Now, either way we look at it, whether we're looking at Kc or whether we're looking at the percent reaction, Kc is significantly lower than 1. The percent reaction is significantly lower than 50%. Both of those pieces of evidence tell us that the reactants were favored, and that at equilibrium there was proportionally more reactant than there was product in the container.